in a third and concluding session on the webinar series that we named Advances in Material Science and Engineering. We realized that material science is an evolving field of research, and it is accommodating a broad discipline of expertise. So in this webinar, what we try to do, we try to make it little different from other seminars. Here, actually, we wanted to listen from one of the expert and the other talk from a budding researcher. So we had total 3 sessions. Already we have heard 4 exciting lectures, and today we have Professor Mallar Roy and Mr. Nipun Sharma. So I'm not taking much of your time. Let us start today's session. And now I'm handing over this Zoom platform to my INYAS colleague, Dr. Chirosri Roy Chaudhary from IIST Shibpur, to introduce the first speaker of today's session, Professor Mallar Roy. Chirosri, please.
Okay, so thank you, Sripanna, for the brief introduction about the webinar series. So it's my pleasure to introduce Professor Mallar Roy, who was my colleague at IIST Shibpur. He's presently a research professor in the School of Engineering and Sciences of Tec de Monterrey at Mexico. He did his graduation and post-graduation in physics from University of Calcutta. And then he again proceeded to obtain a second postgraduate degree from University of Nottingham as a British traveling scholar. Thereafter, he did his doctoral research in the area of silicon nanostructures and its applications from BESU Shibpur. IIST was actually previously BESU. And his primary research interest is on experimental and theoretical investigations on semiconductor and hybrid nanostructures, with focus on understanding their size-dependent optical and transport properties. He was always a very popular teacher amongst his students, and he's also a prolific speaker. So I do not want to take much of his time. So yes, Professor Mallar Roy, so it's all yours. You can start your presentation.
Thank you so much, Dr. Roy Chaudhary, Dr. Chatterjee, Dr. Praveen, for first of all, for inviting me to this webinar series. I'm truly grateful to you all because, as you all heard, that right now I'm in Mexico. I'm working in this university called Tecnológico de Monterrey, but I have very strong connections with India, which I cherish, which I want to maintain and continue. So I'm truly delighted to be part of this webinar series and address the youth members of the Indian National Science Academy. So that is truly a great pleasure, and thank you again for inviting me to this talk. So what I want to talk today, what I want to present today is about something which is not as popular as other nanostructures. I'd like to talk to you about amorphous nanostructures based on carbon. And we will see that although they're amorphous, there are some very interesting and exciting properties that we get out of these amorphous nanostructures. So what you see in the background of this slide is precisely my university. So it's at the end of the talk, I'll take about a few minutes to kind of advertise about my university. But these two buildings, these two kind of tilted buildings that you see, which is here popularly called the napkin holder buildings, these buildings presently house our laboratories as well as my office. And as you can well imagine, that this is not a photoshopped image. So it is located in a very beautiful, picturesque background. Well, I am Mallar Roy, and this is my email. I invite all of you to write to me and get in touch with me regarding this talk and any other future prospects in research that we do. Well, in order to introduce this subject, and also because I know that's what Dr. Roy Chaudhary and Dr. Chatterjee told me, that mostly here the participants are young researchers who have just started their doctoral studies, I'll start with something very basic, which all of you know, just to set the perspective of this talk. So I'm talking about nanostructures, and all of you know, everyone, even people who are not even remotely connected to nano, they know what is nano. That nano is something to do with 10 to the power minus 9, and it is just a scale. But when we say about nanomaterials or nanotechnology, we are not just concerned about any nanoscale, we are concerned about the length scale of 10 to the power minus 9. So the first question which should arise in the mind of any researcher trying to begin work in this field of nanoscience and nanotechnology is, what is so special about 10 to the power minus 9? We all know this, but it would be good to refresh our memories a little bit. Now we know that materials around us, all materials that we see, the bulk materials, they can be as mundane as something like coal or things that we eat, gold, silver. All these materials are characterized by material properties. These properties can be mechanical properties, optical properties, electrical properties, magnetic properties, and they are the bulk materials. And we also know that these bulk materials, the solid materials, are mostly typically crystals. And the length scale of crystals in a bulk is typically of the order of microns. Maybe 1 micron, maybe 100 microns, maybe millimeters, but typically in the micron range. And as we all know that these crystals are all made up of atoms, and the length scale of the atoms is in the range of angstroms. We all know that. Starting from hydrogen to uranium, wherever you go, they're typically of the order of angstroms. And of course, nucleus is of the order of femtometers, or hundreds of tens of femtometers. So where does nano feature in here? All these constituent particles of matter and their length scale are kind of known to us. So nano, of course, is somewhere in between. Somewhere where it's not as bulk as a typical crystal that we see, but not as small as atoms. So it's very easy to imagine at the very first go that this world of nanostructures and nanomaterials would have characteristics which is intermediate to that of a bulk crystal and to that of individual atoms. But a central question that we should ask is, what happens to materials' properties? Because, okay, let's think of any material property that could come to our mind. For example, let's say boiling point, melting point, Young's modulus, refractive index, susceptibility, permeability, whatever we think of. Now, all these are essentially thermodynamic properties. We can define, we can measure, we can quantify them when we have a bulk system. Now, it is meaningless, of course, we know, to ask what is the melting point of an atom, or what is the Young's modulus of an atom, or what is the susceptibility of a molecule. I mean, we can in case of susceptibility, but refractive index. So these questions, most of these questions which relate to measurement and understanding of bulk thermodynamic properties, they become meaningless at the level of atoms. So somewhere in between, when we are dealing with countable number of atoms in the nano world, in nanostructures, most of these material properties, at times, it's very difficult not even to measure, but also to define them. Also to define what do we mean if we have, say, a small quasi-zero dimensional structure, what do I mean by its electrical or magnetic properties? Because any meaning, imposing any meaning, would first impose measurements. And measurements are done by bulk apparatus. So what we are getting is a result of all these bulk measurement systems which is working in conjunction with nanostructures. So that makes it quite interesting, quite difficult, and at times very important applications spring out of this that we all know. So the essential thing that we want to highlight here, that all nanomaterials are kind of intermediate between atoms and bulk. Now this is known fact. we also know that at this stage, what we can do is to make most of these material properties, which are otherwise independent of size when they're bulk, all these material properties, let's say we are talking about conductivity, we are talking about refractive index, reflectivity, Young's modulus, magnetic susceptibility, these are material properties. We don't refer to what quantity of water it is when we say that melting point of ice is 0 degree. It doesn't matter whether it's a bucket or whether it's a small cube. But at the nanoscale, these material properties, we all know they become dependent on size. But an important feature here is, why do they become size dependent? In many cases, the size dependent properties can be largely explained purely from a classical viewpoint. We don't require, in certain cases, quantum mechanics. Just by taking a large number of atoms sitting on the surface compared to what is there inside, many of these properties can be explained. For example, it's very popular to work with gold nanoparticles, very easy to make, gold and silver, and you all know that size-dependent plasmonic features of gold properties, and you can get these fantastic colors, and that have been used for thousands of years. The human civilization knew how to make gold nanoparticles. But these characteristics, the plasmonic colors, can be essentially explained in light of classical electromagnetic theory, although the plasmon modes are quantized. On the other hand, if you look at a typical change of conductivity of copper when their size is reduced, from highly conducting copper to non-conducting copper made of nanoparticles of copper, and there's a huge change in conductivity. Here we cannot explain it in terms of classical. It's a typical quantum mechanical phenomena. Even when, like, this is a typical thing which I worked during my PhD, and then some of my students worked. Also, Dr. Rai Chaudhuri worked on it, like silicon nanocrystals, which we can get in different ways, and they can emit light. And these silicon nanocrystals and their properties can only be explained if we can understand the phenomena in the light of quantum mechanical changes, in the light of quantum mechanical effects. So it's important to understand what happens to the size-dependent property, whether they're classical or whether they're quantum. But whatever be it, in a nanomaterial, it's always tuning the properties by tailoring size, or tailoring the properties by tuning size. But since you are all researchers who have just started your journey in research in nanoparticles, in nanomaterials, we all know that the properties of these nanosystems are not only dependent or not only dictated by size. They are also very sensitively dependent on shape. And this shape effect can at times be explained in terms of size. So they are interrelated. One is a function of the other in many cases. But if you have two different structures, say having exactly the same number of atoms, but their shapes are different, quantum mechanical effects predict that their properties would be different. And also, for the given sizes, given shapes, a lot of their properties are dominantly determined by the surface and the defect and defect structures. But these are things which in many cases are beyond our control. When we are making nanoparticles or nanosystems in our laboratory using a variety of techniques, although in certain cases it might be possible to control size, it is very difficult to control shape, their exact surface features, their defects and defect distribution. Now, why am I saying all these basic things? Is to set the perspective of what we are going to discuss now about amorphous nanostructures of carbon, which are called amorphous carbon dots. Now you see, the whole perspective that we presented started from reducing the size of a crystal. Now what happens in case of amorphous, where there is typically no order in the structure that we see? Now our inherent love, I believe, is always for crystalline materials. If I place these two structures in front of you, I guess 100% of us will be attracted towards the crystalline variant rather than the amorphous variant. But if you think in terms of utility, the amorphous variant is till now unfortunately running the society. We are all driven by the energy that is derived out of coal rather than the fantastic features of crystalline diamond. So academically also, from the point of view of research, most of our research efforts, more than 90% of our research efforts, have been focused on crystalline materials. Comparatively, almost nothing has been done on amorphous structures. So put this in the realm of the different types of carbon allotropes that we know. Again, I guess this is something which is elementary for most of you, that the basic building block of most of these structures is considered to be graphene, which is an ideal 2D hexagonal honeycomb structure of carbon. You put them, stack them together and make them a bulk, and that is graphite. Roll them in one, you get a carbon nanotube. Into many, you get multiple wall carbon nanotubes. This is a typically different diamond structure, which you can get again out of these carbon. You can have fullerenes, different types of quasi-zero dimensional carbon. But in addition to that, what we have, or what we can have in principle, is an assortment of carbon atoms without any apparent order in them. And these are typically amorphous structures, which is the dominant form in most of the variants of coal, where we don't see much order even at the microscopic level. Now, in terms of zero-dimensional or quasi-zero-dimensional carbon structures, there were at least 3 variants which were very well studied for the last almost 20 years, nearly 20 years. One of them, which has been hitting the headlines for the last 10 years or 15 years, are the graphene quantum dots. Now, what are these graphene quantum dots? They are actually small pieces of graphene, ideally one monolayer or a few monolayers stacked one on the other, but these are small pieces of graphene. There is something else which are called carbon quantum dots. Now, these carbon quantum dots are actually larger. They're typically small pieces of graphite. So they have many stacked layers of graphene in them, or some enclosure which straps several layers of crystalline graphene, and they are crystalline. In addition, we could have polymer dots, which are dominantly carbon, but also, they have hydrogen, oxygen, nitrogen in certain cases, which is like a ball of wool. You have long polymer chains wrapped up in a kind of wool, and those are called polymer dots. But in addition to that, which we believe that one of our group is one of the groups to introduce, are just small clusters of carbon atoms bereft of any crystalline order. These are amorphous clusters, and they are called amorphous carbon dots. But how do they look like? I mean, if I look at just this bright field micrograph, most of them look very similar under a transmission electron microscope. But a closer inspection of graphene quantum dots would definitely give you a crystalline structure, and the diffraction pattern would give you some diffraction reinforced areas consisting usually of rings because of randomly oriented nanocrystals. But the essential feature of graphene quantum dots is that they will have some signature of order, crystallinity. Okay? The carbon quantum dots, similarly, as I said, that they are usually larger than the graphene quantum dots because inside them you have small flakes of graphene, and they are crystalline. Now, polymer quantum dots can be crystalline, may not be crystalline. Both of them are possible. If you have long polymer chain rolled up in a kind of manner which induces some kind of periodicity, you get crystalline signature. Or a ball of wool just crumpled together, you don't get crystalline signature. But nevertheless, they are essentially polymers. They are long chain carbon molecules. Whereas in case of amorphous dots, if I just look at their TEM images, it will be very hard to distinguish them from the graphene dots or even the carbon quantum dots in certain cases. But the structures that we made in our laboratory, in a very simple way, I'll go through it. They macroscopically, I mean, not macroscopically as in macro, but just looking at the image, they look like graphene dots. But every time we tried to get an electron diffraction pattern or trying to look at the fringes, we failed. But that was not conclusive. So we had to do some other experiments like electron energy loss spectroscopy, which can show some signature peaks of crystalline order. But all these attempts, we failed. We never found any crystalline order in any of these structures that we made, which forced us to conclude that these are kind of random arrangement of clusters of carbon atom, which are kind of caged maybe by some surface functional groups. Now, these surface functional groups are important. I'm not going into the details of that, but we can easily find out these surface functional groups by doing studies like X-ray photoemission spectroscopy, and we can find out exactly what the surface functional groups are, which are keeping this random arrangement of carbon atoms together. But how are they formed? A standard route of forming carbon nanostructures, this is not the only route, but standard route can be divided into three very basic steps. The first step involves pyrolysis of carbon-rich precursors. In fact, there was a paper published back in 2012 by a very prolific group, and they said that any carbohydrate containing carbon, hydrogen, and oxygen in the ratio of 1 to 2:1, they can be converted into carbon nanostructures, graphene dots, or carbon quantum dots. And it's very easy. All you need is a very simple apparatus in your laboratory. We know that many of the labs are kind of short in facilities, but these are things which you can make essentially with a beaker and some hot plates. Very simple things. The first step is pyrolysis, followed by carbonization and nucleation. And then, if you want, you can passivate the surface with stabilizing agent, or they can be self-stabilized, self-passivating. So, most of these carbon nanostructures can be formed in this way. But when we want to form amorphous, when we don't want to induce crystallinity in them, what do? The simple thing is we don't go high up in that energy where we can push these carbon atoms to reorient and get a crystalline structure in them. So we do the whole experiment in a comparatively lower energy regime. So the particular experiment that led us to form these amorphous clusters was done in room temperature. We replaced pyrolysis by simple, very long-term ultrasonic agitation of carbon precursors. We can do it with glucose, dextrose, we can even do it with coal. Of course, it requires purification, which again leads to carbonization, nucleation, and then surface passivation. In fact, we are able to passivate it by the reagents which are already present, like hydrogen, carbon, oxygen. We can also passivate from outside by, say, amines, or by nitrogen-containing groups, or sulfur-containing groups, or many other groups. Why do we do that? Because we want to see what are the difference in properties as compared to a carbon cluster which is not passivated externally by some group, and when we have some external groups and that. What is the role of the surface? What are their properties like? Well, we do this. But what is highly this is just a surface characteristic of these carbon clusters. X-ray photoelectron spectroscopy, photoemission spectroscopy. And these are the elemental mapping, which clearly shows we have a central region of carbon surrounded essentially by hydrogen and oxygen, which are not very, very homogeneously distributed, but somehow encapsulating that cluster of carbon atoms. So one very important question would be, are these stable? Or do we put them in some and stir them again and they become just isolated atoms and molecules of carbon? How do we know that? Well, one way of knowing that is to investigate their properties. And one of the key properties, we have been studying both electrical and optical properties of these nanoparticles. We have just started with some magnetic measurements. But I will just tell you about very simple optical properties of these carbon dots. Now, these carbon dots, like the graphene dots, like carbon quantum dots, they are luminescent, which means they emit light whenever they are excited by some external energy sources. And a typical experiment, very easy to do in the lab, is to do photoluminescence experiment. So you excite it with a laser or any high energetic radiation, and we can see with our bare eyes that they emit light, they glow. Usually they glow in the blue if you are exciting with UV. But if we change the excitation energy, if we say reduce the excitation energy from ultraviolet all the way to blue to green, we can essentially tailor the output emission that we get from these carbon dots, all the way from blue to nearly red emission. That's what we see in the picture, and that is also what is reflected in the emission spectrograph. Now, this kind of feature was very well known for the graphene dots. And in fact, it's simple to make graphene dots, small pieces of graphene in a colloidal suspension. And to our amazement, when we compared their optical properties of the graphene quantum dots and the amorphous quantum dots, we saw a striking similarity between them as far as their optical properties are concerned. These graphene quantum dots, which are much more difficult to make, more exotic, and these amorphous clusters of carbon dots, their photoluminescent emission spectrum, their UV visible absorption spectrum, their photoluminescence excitation spectrum, their quantum yields, they're almost comparable. Now that posed a question to us, because the physics of emission in case of crystalline materials is much well understood, although there is still a problem in understanding the exact mechanism involved in graphene dots, in carbon quantum dots. But what happens in an amorphous cluster? What is the physics? Because those who have a basic background in quantum would know that we know what happens to the electronic energy structure if we have a periodic arrangement of atoms. But what happens if we just destroy that periodicity? We have random collections of atoms, more or less random collections of atoms. What happens to the electronic energy structure? What happens to the band gap? How do we tailor them? How do they all arise? Now this whole thing gives rise to a kind of demand for a new theoretical structure which would be able to explain the behaviors of these amorphous systems. Okay? Now here, I would just break for one moment to take you from carbon to the world of silicon. We know they have similarities. They are tetravalent elemental semiconductors in general, but they are completely two different materials. I was telling you probably that my PhD and PhD of my first PhD scholar were based on silicon nanostructures. Now these silicon nanostructures we made in a different way. We made it by repetitive, oxidation etching of a ball meal sample, a very crude way of making it. But in that crude way, we could get a nearly well-distributed quasi-zero-dimensional silicon quantum dots whose structures are typically 2 nanometers to 10 nanometers. And these silicon quantum dots also emit light. And interestingly, the emission pattern of the silicon quantum dots are very similar to the emission patterns that we obtain in carbon. Now, why is it so? Now, some of you might know, if you're working with silicon and carbon, there have been research on photoluminescence from silicon for the last 30 years. Many groups in the world worked on it. Many groups in the world are working on carbon dots, graphene quantum dots. But till now, we do not have a conclusive understanding of the emission mechanism that is operative in carbon and silicon systems. So this kind of uncanny similarity between silicon and carbon dots, in my opinion, gives us more food for thought to think what exactly might be happening. Now, one very easy key answer would be, okay, these dots are not playing the role, it's the surface species. But let me tell you that there have been many works. In fact, we have also spent almost 10 years in trying to understand what exactly is the role of the surface species. But it is not emission only from the surface species, which I can assure from the experience that we have done. So it's not the surface. It's silicon and carbon are not, scaffolds of some chromophores which are on the surface. They also have a role to play. Surface definitely has a role to play in conjunction to what is there in the core. So this is still an active area of research, and I believe some of you might be interested in this field and to carry it forward to some conclusive understanding in this emission mechanism. But students and researchers with more engineering bent of mind would probably ask the question that, okay, we don't know the mechanism, the physics might be very complicated and interesting, but what do we do with them? Well, there have been many studies, many propositions, but this is an interesting article which was again published several years back, which pointed out that the optical properties of these carbon dots, the graphene dots, carbon quantum dots, they have huge application potential. And this is what Professor Ferrari and his group points out in this review paper published in Nature Photonics. And much of these potential have not been realized. So there are, in fact, application potentials. I will just show you here some very few basic preliminary application that we could do in our lab using these amorphous carbon nanostructures. The first one is a simple thing. It was detection of a nitroaromatic. Of course, we cannot work with TNT in lab, so we work with TNP, that is trinitrophenol. And we could see that these amorphous carbon dots, by suitable tailoring of the surface species, and we needed a little bit of chemistry in that, so I took help of colleagues working in chemistry to attach suitable surface species which are very sensitive and can specifically attach to TNP. And we could see that it could extremely sensitively and selectively detect TNP, and one of the best, or if not the best, that have ever been recorded. And the mechanism of detection is simply based on quenching of the luminescence intensity. We didn't make a device out of it, but we made a device out of something else where we could actually measure the concentration simply by using a paper, like a pH paper, the way you measure pH, we could measure the concentration looking at the color change, and we can quantify that from the PL spectrum. So that is one very simple application. Another application is making invisible fluorescent ink. Again, many structures have been used, many kind of nanostructures have been used, dyes have been used to make fluorescent ink, but these carbon dots are also exciting materials to make invisible inks. So we can write on a paper which is not visible under ordinary light, but if you shine UV light, you can see what is written on them. Now that is simple. That some of you who work on this field would know that that's not difficult to do. But what is difficult here, to get an ink, get an invisible ink which can write on any possible surface. It can write on a transparency, on a slide, this is just a tissue paper. It can write on ceramic, it can write on a metal, it can write on silicon, it can write on nearly all kinds of surfaces that we know about. And importantly, it can write without smudging. But, it was not as simple. We had to attach certain specific molecules to the surface of these carbon dots, and we did a smudge test. I won't show you the whole video, that's kind of boring. And we did a smudge test by seeing two different inks, a standard ink and the ink made of carbon dots, and we showed that these inks do not smudge, which is a very important requirement for getting prints for anti-counterfeiting purposes in currency notes. So these fluorescent carbon dots are important materials, can be important materials for using as anti-counterfeiting materials in notes, particularly because of their smudge resistance, and also, of course, being invisible under ordinary light and visible under excitation. Now, these are kind of non-exotic applications. One application which some of my colleagues working in biofield said that, okay, if you can get them encapsulated into kind of films, then we can use these films to load materials and do biological experiments. So the first thing that we did was to simply mix it in certain ratios with chitosan, and we could make films with very good mechanical properties, which is one of the principal requirements for applications of these films in the biological fields, that they should be mechanically stable. And these films are easy to make, of course, much less expensive than the more exotic crystalline counterparts, and their mechanical properties are comparable and sometimes better than the films that you make out of the graphene quantum dots in chitosan. Now, I will end this with the most recent work on these dots, where we have put these dots in gelma, gelatine with acrylate. Well, don't ask me a lot about this because I don't know the biological part of it, but I have colleagues here working actively in fields of biotechnology and medicine. So what we could do, we could use microfluidics to make micron size spherical particles of gelma that people can make. We can control their sizes. But using microfluidic techniques, we could embed this gelma with these luminescent carbon dots. So what is the advantage of this? The first advantage of this makes gelma microgels, which have many applications in biology, in tissue engineering, in scaffolds. It makes them easily tractable, right? So if you are doing an experiment in vivo or in vitro, whatever, you can just shine blue light, not even violet. These are experiments done by shining 405, that is 405 nanometer light. That's violet light. And you get a luminescence out. So you can easily track them throughout the course of your experiment. And that produced a 3D cultural platform which encapsulated both the carbon dots and skeletal muscle cells. And we tested their cytocompatibility and cell viability. And amazingly, we don't know the science behind it right now, they showed very impressive cell viability and myogenic differentiation of C2, C12 myoblasts, which are encapsulated in this gelma microgels. Okay, so this is a work which is almost nearing its completion, and what we see that these apparently mundane, uninteresting, aperiodic, non-existing carbon dots can have very interesting applications, and most importantly to me, the physics of it has many new things to offer. So this is where I will end my technical talk, but I'll take the last couple of minutes to a bit of advertise my present university where I'm working for the last 2 years. First, some numbers about my university, that it is ranked among like 155, 129 in engineering and technology. It is number 1 in Mexico. But you know, all these are numbers. But numbers are not very relevant, but at least they give you some indicators. That this university is, being a university in Mexico, and Mexico is similar to India, not like India, but very similar to India. But it is a growing university. It has been growing, and we all aspire that it will soon improve much in terms of its rank, in terms of its research outputs. So research output has been quite fascinating. I was very impressed. In fact, I was telling Chirosri, I was a bit surprised that when they offered me a job and I came here, and I'm very surprised by this university. It has a it has an excellent ambience. This is a library, and this is the view, what you get from one of the reading areas in the library. Interestingly, there are places inside the library. I remember that when we were students, we used to get a scolding from our teachers if we laid our head down or we were sleepy. But here, students are encouraged to sleep. I mean, there are sleeping mattresses in certain areas where you can go and sleep if you want to. And there are students spending day and night. There are pianos thrown around. If you just want to leisure, you can go and play the piano and things like that. It is a fantastic stadium, fantastic auditorium. So these are all kind of things which I want to tell you to lure you. Why? The reason is because we have open funded PhD positions in material science and engineering. But as Dr. Chatterjee said at the very beginning of this webinar, as an introduction, that we are introducing, this is a part of the webinar in material science and engineering, and I belong to material science and engineering. And for me, what does it mean? And that's kind of the conclusion, that science in general, we know, is when you know why and how things work. but it cannot make things work in reality. For example, I mean, knowing about the electronic energy structure in these carbons, we are interested in why. That's what a typical physicist, a scientist would try to do, try to know why. And engineering is all about making things work, but you do not know how and why. For example, you have these carbon dots, you can put them in GELMA, you can do cell differentiation, you can do cell viability tests, but you don't know exactly how they're working. But that's engineering, right? Now, what do we do in material science and engineering in my group? I'm not taking the responsibility of the other groups. In our lab, we have combined science and engineering, which means we cannot make things work in reality, and we do not know why. Okay? So thank you very much. I'd like to acknowledge my erstwhile PhD student, Abu Siddiqui, and Professor Sergio Martinez, my colleague here. So thank you all. I think I'm in time.
Yeah. So thank you, Dr. Ray. Myself, Dr. Bashpai. A wonderful talk, sir. Extensively covering the amorphous carbon dots and their processing and properties, along with its application in your research, and especially you showed that the invisible fluorescent ink sensing devices and luminescent field. So for the audience, the talk is now open for the discussion. Anybody has, so please unmute yourself and you can ask the questions.
Yes, sir. So this is Sumit.
Yes, please.
Sir, you have discussed about amorphous quantum dot and crystalline quantum dot. So my question is, sir, how can I differentiate crystalline quantum dot and amorphous quantum dot by using any material characterization technique?
Okay, good. First thing, thank you for the question. First thing I would like to point out is about the nomenclature. Whether, if you have noted, I have not referred these amorphous nanostructures as quantum dots ever. Now, this relates to your question that unless we are very sure of quantum mechanical effects in these nanoparticles, we don't call them quantum dots. We call them nanoparticles, nanostructures, just dots. So these amorphous clusters of carbon, till now, we are calling them only carbon dots. We are not calling them carbon quantum dots. Whereas the graphene dots, we know it for sure that they have quantum mechanical effects. So we call them graphene quantum dots. The carbon quantum dots. First distinguishing feature. That's the physics answer. Now the engineering answer, how do we know? Well, of course, we have to look for signatures of crystallinity very thoroughly. Now that's what we did. If you remember that we tried to look at first diffraction patterns. If we get, you can do micro diffraction using the diffraction in your transmission electron microscope. If you do not get any electron diffraction pattern out of these structures, you can do it very locally also, then definitely that is suggestive that there is no crystallinity, or there is any lack of crystallinity that we can detect. There may be crystallinity at a finer order, maybe at the length scale of 1 nanometer. We don't know. But if we can detect up to the level of 5-10 nanometers and we don't get any detectable crystallinity, that's good enough reason to conclude. We also did it with electron energy loss spectroscopy, and that is a typical way of finding out, because this electron loss spectroscopy, electron energy loss, how electron loses their energy when they are bombarded against that structure, they have signatures, these outgoing electrons, whether they are scattered from a periodic structure or whether they are scattered from an amorphous structure. So this energy loss spectroscopy also gives us information about whether they're crystalline or amorphous. But I would not strongly believe results of X-ray diffraction, because X-ray diffraction, even if you have very small nanocrystals, in many cases you don't get kind of crystalline peaks. So X-ray diffraction, not always reliable for ultra small nanocrystals. But electron diffraction, local, yes. Electron energy loss spectroscopy, yes. And there may be other techniques which, there are other techniques to infer about crystallinity. But these two are kind of conclusive at this level. But that does not mean that there is no periodicity beyond the level that we have investigated. Does that answer your question?
Yes, sir. Yes, sir. I got it, sir. Thank you so much.
Thank you.
May I ask one question?
Absolutely. Thank you so much.
Yes. So my question is like, we generally want to synthesize crystalline material, and sometimes we end up in preparing some amorphous material, and at that time we get disappointed. Okay, so when we don't get nice crystalline peaks in XRD. But in your case, purposefully, you are synthesizing amorphous material. So, there is like two parts. So first question, my question is that how do you control this amorphosity in these nanomaterials? And the second thing is that you have shown nice optical property. So, like if I compare this fluorescence property of this amorphous and the crystalline, like same, let it be carbon dot or let it be silicon dot. Is there any difference or improvement or means anything? And what will be your comment on this?
Excellent. Okay, so let me take the first question. How do we control? The first honest answer would be we have little control over their size, over their, essentially their size and size distribution. We could not tailor it by a large extent. Nearly every time we do, we get this amazingly, the distribution is well defined. It's kind of from 2 to 10 nanometers. We have done, umpteen number of micrographs using TEM. It's very well distributed, but it's very difficult to make them bigger. We can't, for example, make 20 nanometers or 30 nanometers amorphous clusters. The moment we try to do that, and we have tried many techniques, they tend to form crystalline structures. So that's a problem. We don't have much control. First, control over their size. But we can control the surface. That is simply mixing different surface passivating reagents in the hydrothermal reactor and things like that. So that answers your first question, that we do not have control over the size in terms of long-range size distribution. It's always typically very small. Now, how do we control the amorphous nature? That is something not going at high temperature. It's basically temperature, room temperature, and for carbon dots, we just do ultrasonication. We are trying to do this with silicon, met with very limited success till now, to get dominantly amorphous crystalline, amorphous islands of silicon. So I'm not talking about that. But in case of carbon, if you don't raise the temperature, if you do it in room temperature, ultrasonicate for a very long time, we have been playing around with the time, playing around with certain stabilizing agents. But every time we do, we get the same thing. But it's amorphous. Amorphous is controlled by temperature. That's what we can say. Now, the other question that you asked is, what are the differences in their optical properties? Well, yes, since this was more of a popular talk, I pointed mostly towards the similarities, but there are differences. In fact, we have a last paper on that, pointing out the differences between amorphous carbon dots, crystalline carbon dots, and graphene dots. So they have differences, but these differences are not in-your-face difference. There are subtle differences. A major difference, of course, is in quantum yield. Now, for graphene dots, if we have specific nitrogen groups, particularly amine, then we can have a huge quantum yield. Huge meaning huge, 90% or more. And there are reports. In fact, there's a report of nitrogen passivated graphene dot claiming 97% quantum yield. Now, this happens because of a typical role that these amines or nitrogen plays in introducing some metastable states inside the band gap of graphene, or enlarged band gap of graphene dots. Graphene itself is zero band gap. But in case of amorphous, again, as we have little control over their size and consequently their electronic energy structure, we cannot have a huge variation in their quantum yield. But we could push up the quantum yield beyond 10%, which is very decent for this amorphous quantum dot. So a major difference is in the quantum yield. Another difference is in how the emission spectrum varies with the excitation energy. In case of amorphous quantum dots, we see nearly a consistent variation of the emitted energy as we change the excitation. But this is not exactly so for different kinds of graphene dots. There are different kinds of graphene dots which show excitation dependent and then excitation independence. We can, in fact, fix the excitation dependence and make it excitation independent by suitable surface functionalizations. It also depends on where this amine group is, on whether it is somewhere inside or on the surface, and there are theoretical calculations done on that, though we don't have experimental control. So there are some differences, but those differences at this level are more subtle. So yes, it's right that there are differences, and I didn't talk about it much. So thank you.
Thank
I have
you.
a small question.
Yes, Yusri.
Yeah. Have you explored the electrical properties of this amorphous carbon dots and compared it with the so-called crystalline carbon quantum dots?
Yeah, that's also a very interesting and obvious question. Till now, no.
Okay.
The problem, that how to measure electrical properties. I mean, one would be what we really want to do is to do a single dot measurement
Yes.
using SPM probes. Now
Yes.
that, you understand, is very challenging. First of all, to get a single dot on a specific substrate, and it's mostly dominated by the SPM probe current. So that is very challenging. The other would be
If you make a film, I don't know, like
make a
in
film, but
various.
then these film properties are overwhelmingly dominated by the film formation parameters, which is basically the porosity. So if we can always have a film where these dots are kind of compact and we can control this,
Yeah.
then yes, films would be good. Or we can also pelletize them to form pellets and look at them. But then pelletization conditions again they are almost always dominated by the inter-dot geometry. Inter-dot geometry. What we did actually, and that has another implication, we got these dots inside a common matrix. And in this case, we are using conducting polymer matrix because we want to tailor some other properties of that. So in this conducting polymer matrix, we put in graphene dots, we put in carbon dots, and we are also trying with amorphous carbon dots, keeping the matrix same and looking at the macroscopic charge transport characteristics of these composites. So that is something which we are exploring, but till now with amorphous, we have not done any measurements. But that is a very interesting topic, of course, to look at the electrical transport through an ensemble of this amorphous carbon dots.
Yeah, because carbon quantum dots, crystalline carbon quantum dots have been used for electrochemical sensing for quite some time, and they are very promising candidates in terms of cost and affordability issues and all that. So I think amorphous dots will be much more easier to make in that sense.
Yes. For electrochemical sensing, we can use it. I mean, they can be used as colloids. That is something which we can always do. But I was talking about a macroscopic bulk IV characteristics that.
Oh, okay.
Good.
Sir, I have one small question. What is the level of yield? Yield means you have shown that we can make ink out of it. So can we make paste out of it?
Yes, we can. I mean, that essentially depends on how much water we can drive out of it. So in fact, after we make it and we keep it, it's more like a, what should I say? It's like a gel, like a paste. And we take a certain amount of it and then we sonicate in water to get colloidal suspensions. So we can make paste out of it.
Thank you. Yeah, so if I don't think that any other further question. So now I thank you, sir, once again.
Thank you
And
so much. Thank you so much for the invitation. Bye.
I will now